Welcome to The Curious Machine. Today, we're diving into, well, a riddle, one that has roots way back in ancient history, and it really sets the stage perfectly for our deep dive. Picture this, the biblical account of Henry's basin for King Solomon's temple. It's described as having a diameter of 10 cubits and a circumference of 30 cubits.
Right. And if you spent even like half an hour with basic geometry, you immediately sense something's a bit off there. Those numbers, they feel almost too neat, don't they?
They really do because, well, there's this fundamental ratio. It's universal for every single circle, doesn't matter how big or small. It links the circumference directly to the diameter. We call it pi, the Greek letter. And its value is approximately 3.14159, give or take. So, yeah, a 10-cubit diameter circle. It should actually have a circumference closer to 31.4 cubits, not this perfect 30.
It is kind of charming, in a way, to think that maybe even a sacred text might just round pi down to a simple 3. But what's really interesting is that other parts of that same text, they actually use half measurements, things like 2.5 or 1.5 cubits. So that tells us that precise non-rounded numbers were definitely part of their system. It wasn't just rounding for convenience.
Exactly. And today, March 14th, is often celebrated as Pi Day, 314. You've probably seen the usual fun facts, maybe a few pi jokes online. But here we want to go, well, a lot deeper than that surface level stuff.
Yeah, our mission today is really to uncover 7 fascinating, maybe lesser-known aspects of pi. We want to show you why this number, this constant, is so much more profound, more pervasive than just circles, and how it kind of quietly shapes our world in some really unexpected ways. So yeah, let's start exploring.
Okay, so our first stop is ancient Greece. And this problem that, honestly, it obsessed mathematicians for centuries. It's called squaring the circle. Imagine trying to draw a square that has the exact same area as a circle you're given. But here's the catch. You can only use 2 tools. A simple straight edge, like a ruler with no markings, and a compass for drawing circles and arcs. That's it.
And for the Greeks, this wasn't just like a geometry puzzle. It was much deeper. It became this kind of philosophical quest, almost searching for a perfect harmony between the circle, seen as divine maybe, and the square, more earthly. But it also had practical sides, surprisingly. Things like dividing land fairly or planning agriculture.
It's pretty amazing when you think about the tools they did have, though. The Greeks were masters of basic arithmetic, adding, subtracting. They even had clever ways to multiply using proportional triangles. And they could even figure out square roots using this really neat method involving a semicircle. But here's the kicker, the huge missing piece. They had no algebra. 0. It's hard to even imagine math without the concept of x, isn't it?
Really, because they couldn't just set up an equation like, area of circle is pi r squared, area of square is a squared, so a must be r times the square root of pi.
Yeah.
That whole algebraic way of thinking just didn't exist for them yet. And it's precisely because of those limitations, the tools they didn't have, that they could never actually solve it. But grappling with this problem for so long forced a much, much deeper understanding of what pi itself actually is.
Which leads us perfectly to our second point. Pi's really mysterious nature. We all learn it starts 3.14159. But what does it truly mean when mathematicians say pi is irrational?
Right. Well, irrational in math doesn't mean illogical or crazy. It literally means unratioable. It's a number that you simply cannot express perfectly as a ratio of 2 whole numbers, like a simple fraction. Think about 22 divided by 7. It's a decent approximation for pi, sure. But if you actually do the division, the decimal digits eventually start repeating in a pattern. Pi, on the other hand, its decimal digits go on forever, and they never repeat in any discernible pattern. It behaves a lot like a sequence of random numbers, statistically speaking, though it actually hasn't been formally proven to be perfectly normal, which is a technical term meaning all digits appear with exactly the same frequency in the long run.
That's mind-bending. Just goes on forever. No pattern. And this discovery, it must have caused quite a stir back in ancient Greece. Oh, absolutely. A huge philosophical shockwave. You have the Pythagoreans. Remember them. They believed the universe was built on whole numbers and their nice, neat ratios. Numbers were sacred. Perfect. So the very idea of irrational numbers, numbers that couldn't be contained in these perfect ratios, it was deeply unsettling. There are even these, well, probably exaggerated stories about Hippasus. He supposedly proved the square root of 2 was irrational. And the stories say he was punished for it, maybe even drowned at sea, for revealing this uncomfortable truth. It challenged their whole worldview.
Wow. Okay, so it irrational. But then there's another layer. You mentioned pi is also transcendental. How does that go beyond just being irrational? What does that add to the whole squaring the circle problem? That's a great question. Transcendental adds a really crucial layer of impossibility. So To put it simply, a number is transcendental if it's not the solution to any polynomial equation that has simple whole number coefficients. Think of an equation like x squared minus 2 equals 0. The solution is x equals the square root of 2. Now, the square root of 2 is irrational. We just discussed that. But it's not transcendental because it is the solution to that simple polynomial equation. Pi, however, it cannot be the root of any such polynomial equation with integer coefficients, no matter how complex you make the equation. This abstract mathematical property had a very concrete result. It formally proves, once and for all, that the ancient Greek dream of squaring the circle with just a compass and straight edge is absolutely impossible. And this wasn't proven until, get this, 1882. A mathematician named Ferdinand von Lindemann finally managed it.
1882. So after centuries of trying, Lindemann proves it's impossible, which naturally leads to our next point, because apparently not everyone was thrilled with this proof. It's a fascinating story of belief versus math.
No, definitely not everyone accepted it. Enter Edward J. Goodwin. He was an American physician from Indiana, and he was reportedly quite annoyed by Lindemann's proof. Why? Because the Goodwin believed he had already squared the circle. He even got his findings published. It was in a new math journal that was kind of struggling. And significantly, the editor included a disclaimer basically saying, we're publishing this, but we don't necessarily endorse it.
Okay, that's already a bit strange. But what happened next is almost unbelievable. Goodwin actually used his political connections, and he got a bill introduced in the Indiana House of Representatives. And the goal of this bill, to legally declare his incorrect value of pi as the official one in Indiana. And, to offer his discovery as a free gift to the state's education system. It sounds like satire, but it actually happened.
It really did. And the bill's journey through the legislature was, well, kind of a farce. It got passed around from the Finance Committee to the Committee on Swamps. Yes, literally, swamps. And then somehow ended up in the Education Committee. Why? Because apparently none of the legislators really understood the math involved. They just kept pushing it onto someone else. And incredibly, the bill passed the House unanimously. 0 objections. Think about that. A state legislature passing a law about a fundamental constant of the universe based on incorrect math they admittedly didn't understand.
It really highlights why we need experts sometimes, doesn't it? Thankfully, someone did understand. A mathematician named Clarence Waldo from Purdue University happened to be in the State House that day. He saw what was happening, intervened when the bill got to the Senate, talked to the senators, explained the actual mathematics, and he managed to stop the bill from becoming a law. Just barely.
Yeah, it's such a powerful, almost absurd, real-world example of what can happen when personal conviction, or maybe just ignorance, clashes with objective scientific fact. It's a stark reminder that truth isn't decided by a vote or by passing a law. Mathematical truths are what they are, regardless of what we might want them to be.
Okay, so moving from the, let's say, mathematically challenged to the absolute cutting edge. Our fourth point is about the modern quest for pi. We've gone way beyond just a few decimal places. We're talking trillions now.
It's a staggering leap, isn't it? The game really changed with the arrival of general-purpose computers. Think ENIAC back in the mid-20th century. That just blew the doors open for calculation. The current record holder is Emma Haruka Iwao, working with Google's cloud computing power. She calculated pi to, wait for it, 100 trillion digits.
Yeah.
That computation ran continuously for, I think, about 59 days. Just mind-boggling scale.
100 trillion. But why? I mean, what's the point? Is it just mathematical bragging rights, or is there a deeper reason? Like, how many digits do we actually need for, real-world stuff?
That's the crucial question. And for almost any practical application, the answer is surprisingly few. You only need maybe a few hundred digits for the most demanding cosmological calculations. NASA, for example, they famously used just 15 digits of pi for navigating spacecraft across the solar system. Apparently, with 15 digits, you can calculate the circumference of the entire observable universe to within the width of a few atoms. So yeah, 100 trillion is definitely not for practical precision.
Okay, so if it's not for calculating things, what's the motivation?
It's really about pushing boundaries in other areas. These huge computations are incredibly demanding, so they serve as extreme stress tests for supercomputers, helping to find bugs and limitations in the hardware. They also drive the development of new, highly efficient algorithms for handling enormous numbers. And there's also the pure mathematical curiosity about the digits themselves. Are they truly random-like? People look for patterns, or the lack thereof, like the famous Feynman point that's a sequence of 6 nines in a row that starts at the 762nd decimal place. Studying the distribution of digits is still an active area.
And this pursuit, it sometimes comes with a very human story of effort, and sometimes error, right? like William Shanks.
Ah, yes, poor William Shanks,
Mhm.
a 19th century British mathematician. He spent years of his life calculating pi by hand, meticulously. He got up to 707 decimal places, which was a record at the time. But tragically, it was discovered much later after the advent of calculating machines that he'd made a mistake way back at the 527th digit, which meant all the subsequent 180 digits he calculated were completely wrong. All that effort. It's a sad story, but also, I suppose, a testament to human dedication, even when flawed. A very memorable error.
Definitely. So, beyond calculating it, our fifth point explores how pi just seems to show up everywhere, far beyond circles. It appears in some really surprising places in math and physics, in contexts that seem totally unrelated to geometry.
It really does. It's quite remarkable. For instance, pi is right there in the formula for the period of a simple pendulum. How long it takes for a weight on a string to swing back and forth. It's also embedded in Heisenberg's uncertainty principle in quantum mechanics. That fundamental rule about the limits of knowing a particle's exact position and momentum at the same time. And in engineering, there's Euler's formula for column buckling. It predicts when a slender column will bend under load, and pi is right in there.
It's also in Stokes' law, right? Which deals with friction for objects moving through fluids.
Yeah,
And even in probability, like the chance that if you pick two random whole numbers, they won't share any common factors other than one, that probability involves pi squared.
exactly. The fact that it pops up in fluid dynamics, quantum physics, structural engineering, probability, it just underscores how fundamental pi is. It's not just a property of circles. It seems to be woven into the very mathematical fabric of reality.
Okay, to kind of illustrate how seemingly simple ideas can get complex, let me throw a question at you. We know a triangle has three corners, right? Easy. But how many corners does a semicircle have? Think about it. Is it 0, 2, 3, maybe even infinite?
Huh. That's a great little brain teaser. And the interesting thing is, the answer really depends entirely on how you define corner. If you think of a corner simply as a point where edges meet, well, a semicircle has a curved edge and a straight edge.
Yeah.
They meet at two distinct points, right where the straight line ends. So saying two corners makes perfect sense in that context. If you had a semicircular desk, you'd definitely notice those 2 points.
Okay, 2 seems reasonable, but what about other definitions?
Well, sometimes in geometry, a corner or vertex is defined more strictly as the meeting point of two straight lines, like in a square or a triangle. By that definition, since a semicircle only has one straight edge, it would technically have 0 corners.
0 or 2. Any other possibilities?
Sure, you could take a more abstract view. Think of a circle as a polygon with an infinite number of infinitely small sides. If a full circle has infinitely many corners in that sense, then a semicircle, being half a circle, would still have infinitely many. And, someone might even argue that the very peak of the curve, the point furthest from the straight edge, acts like a third kind of corner. The real point here isn't finding the right answer. It's showing how crucial clear definitions are in mathematics. Pi, in its specific mathematical domain, provides that kind of absolute clarity, unlike our fuzzy concept of a corner.
That makes sense. Definitions matter. Okay, finally, for our 7th point, let's look at pi out in the wild. In popular culture and its sometimes surprising everyday impact, it seems to pop up in the most unexpected places, even apparently in a famous courtroom trial.
That's right. One of Pi's most bizarre public cameos was during the O.J. Simpson trial back in the 90s. The defense attorney, Robert Shapiro, was cross-examining an FBI special agent, Robert Miller, about some scientific evidence. And Shapiro suddenly asked him formula for the area of a circle and then what the value of pi was.
Seriously, in the middle of a murder trial, what happened?
Well, the agent seemed to struggle a bit to recall the exact value on the spot, and then the judge actually jumped in, confidently offering a value, which was slightly incorrect. Now, obviously knowing pi wasn't going to prove guilt or innocence, but as part of the defense's broader strategy, to create doubt, to subtly question the scientific competence and foundational knowledge of the prosecution's experts, it just shows how even something as basic as pi can become a weird footnote in cultural history, used in unexpected ways.
Wild. And beyond courtrooms, pi has a much lighter cultural footprint too, right?
Oh, absolutely. We already mentioned Pi Day on March 14th. There's also Pi Approximation Day on July 22nd for the fraction 227. Then there's this whole subculture of piffleology, people who memorize huge numbers of Pi's digits. Often using mnemonics, these little poems or phrases called poems, where the number of letters in each word corresponds to a digit. Like that classic one, how I want to drink, alcoholic, of course, after the heavy lectures involving quantum mechanics, count the letters 3, 1, 4, 1, 5, 9, 2, 6. The world record holder, Raj Veer Meena, recited 70,000 digits.
70,000, that's incredible dedication. And it shows up in fiction and music too.
Yeah, Carl Sagan famously had a message hidden deep within the digits of pi in his novel Contact. Kate Bush wrote a song called Pi where she sings the digits. And the computer scientist Donald Knuth, he has this fun tradition where the version numbers of his typesetting program, TeX, slowly approach pi over time version 3, then 3.1, 3.14, 3.141, and so on.
That's clever.
And you even have movements challenging pi. There's the tau movement, arguing that 2 times pi, often called tau, is actually the more fundamental circle constant. They celebrate Tau Day on June 28, 628. It all just shows how pi isn't just locked away in textbooks. It's part of our culture, our conversations, even our debates.
Well, there you have it. We've certainly taken a deep dive today. From ancient temple measurements and Greek philosophers trying to square circles, all the way to supercomputers calculating trillions of digits, courtroom antics, and pop songs. It's really clear, isn't it? Pi is so much more than just 3.14, so much more than just a circle thing.
It really is. It feels like a fundamental thread, doesn't it? Woven through math, sure, but also science, history, technology, even culture. It's a fantastic example of how interconnected knowledge can be, how one seemingly simple number can unlock doors to incredibly deep and diverse insights.
So as you go about your day, maybe you'll see a circle somewhere, or maybe even eat some actual pie. Take a moment and think about it. What other things around us, things that seem simple on the surface, numbers, concepts, everyday stuff, might hold similarly profound and unexpected secrets? Secrets just waiting for us to get curious and start digging. Keep those deep dives going.
Thank you very much for sharing this enjoyable conversation with us. Until we meet again tomorrow with a brand new topic, take very good care of yourselves. Goodbye.